All right, a loudspeaker emits sound toward the open end of a pipe, and it sets up a standing wave, right? So outline how a standing wave is formed. We have one mark, but a lot of space, right? What you want to talk about is that there's an incoming wave from the loudspeaker, there's a reflection off the wall, and those either interfere destructively or constructively. So just think about it. So it's one of the two, right? Make those points, right? And then here, draw an arrow on the diagram to represent the direction of the motion of the molecule at x. Well, gee, if this guy is moving to the left, this guy would be moving the opposite direction because of the displacement graph, right? So put a little arrow on there. X is going to be either going to the right or the left. Okay, you decide. Okay, label a position that is a node. A node is where it's not moving. Okay. You already know that though, because you studied that, right? And then the speed of sound is 340 meters per second. The length of the pipe is 0.3 meters. So they're saying that this length right here is 0.30 meters, right? So you're going to set up a 0.30 meters. How many quarter wavelengths do you see here? 1, 2, 3, right? So it's blank quarter wavelengths, right? Solve for the wavelength, okay? Okay. And the wavelength I got is longer than 0.3, okay? But less than 0.4, I'll just say, okay? And then use V as F lambda to find the frequency. You've got, this is 340, this is the number that you just calculated. Solve for that. I got a number between 800 and 900 hertz. Okay. All right. Let's keep going here. Now it's a refraction problem, right? And this is actually a critical angle problem because they're saying give the maximum angle, and the angle is actually this angle right here. These two angles are congruent, right? They're trying to make it look like it's not a critical angle problem, but it is. Okay, and as I increase that angle, and this angle almost certainly is bigger than the angle you'll calculate. Okay, I'm just saying, if they increase this angle, it no longer can escape from the water. And the reason is that, of course, this refracted beam, since it's speeding up, remember this is 340 meters per second. This is 1500 meters per second. I'll call this V1. I'll call that theta 1. I'll call this theta 2, or sorry, that's V2, right? And then here's this, we'll call this angle here theta 2, okay? If this thing is speeding up, remember that this angle here it's bigger and bigger and bigger. When this reaches 90 degrees, the sound can no longer enter the water, okay? When that equals 90 degrees, when this refracted angle, that's what it is, right? So do this. Look in the data packet in section 4.4. You've got this formula, sine theta 2 over sine theta 1 equals V2 over V1. Right? So it's a little different if you use the velocities than it is if you use the indices of refraction. Okay, V1 is this. V2 is this, right? Theta 2, just set that equal to 90 degrees and solve for theta 1. Theta 1 is, I don't know, okay? In degrees, I got a number between 10 and 20, okay? And then it says, draw lines on the diagram to complete the wave fronts A and B in the water for some angle where it can enter the water, right? Okay, so let's take a look at that, right? You already looked at one. If the wavelength, if the velocity decreases, the wavelength would decrease, and those look like this, kind of, right? Like it gets, like imagine that's a straight line, right? Okay, but they could also be like this, right? So you got to decide if it's speeding up, what does it look like, right? I think the wavelength gets bigger. See if you can draw them, right? It's either going to be, this, right, or this, in which case does the wavelength increase? Because the velocity increases by kind of a lot, right? Okay, yeah,